Hello, everybody. Welcome back to Mathematical Statistics. In the last class, we were talking about unbiased estimators with small variance. We were also talking about mean squared error, which I want to talk a little bit more about today. So as you know, if you have a random variable x with a mean mu, then the variance for x, which is a measure of how spread out the distribution of x is the expected value of x minus its mean squared. So for us, we are trying to estimate unknown parameters that are called, let's just say one-dimensional for now, that is called theta. And we are estimating it with a random variable or estimator, theta hat. So the variance of an estimator, theta hat, which is a random variable, is the expected value of the random variable minus its mean. So this is just a kind of much not sloppier, but more cumbersome way to write the line just above when I replace x with theta hat, mostly because I don't have a notation like mu for the mean for theta hat. But that's the variance, and it's exactly what I have on the line above, just different notation. Now, if your estimator is an unbiased estimator, then, so if I have that theta hat is an unbiased estimator for theta, then that expected value in there is just theta. But if this is not the expected value for this, then this entire expression is no longer the variance, because the variance for theta hat is defined in this way. It is the expected squared difference between the estimator and its mean. So in the case that we do not have unbiasedness, this line here is called the MSE, or the mean squared error for theta hat. So if we do have unbiasedness, the variance and the MSE are exactly the same thing. But if we have some bias and we still care about using theta hat as an estimator, then let me draw the picture again. So we've talked about things that have distributions that are nice and centered and are unbiased estimators for theta. And we talked about wanting smaller variance. It's always a better thing. But then we talked a little bit about how about having really small variance with some bias, some trade-off there. If we have a biased estimator, as this green curve represents, then I don't really care about how variable it is, about how much spread I have in here. I care more about how my estimator is away, how far away it is from the thing I'm trying to estimate. So that would be the mean squared error for an estimator of theta. This is the mean of the square of the error between the estimator and the thing I'm trying to estimate. And again, if the expected value of my estimator is theta, then this thing is the variance for theta hat. So variance and MSE are the same when you have an unbiased estimator. If not, we showed a formula last time that the mean squared error for an estimator, theta hat, is the variance for theta hat plus the bias for theta hat squared. And the bias for theta hat is the expected value of theta hat minus the thing you're trying to estimate. So if you have an unbiased estimator, this is theta and this is theta, and the bias is 0, so this goes away, and we get that the MSE equals the variance. But if we've got some bias, then we have a slightly more complicated relationship between the MSE and the variance. So last time we were in the middle of an example, a rather long example, and I'm just going to recap some of this rather than redo it. But we had x1 through xn, IID exponential with rate lambda. And we tried to estimate, well, we ultimately wanted to estimate lambda, but because the mean of this distribution, the mu, the expected value of one of these, is 1 over lambda, and because we know that the sample mean is always an unbiased estimator of the true mean, we did start with this function of lambda rather than lambda itself. And so we have a name for our functions of lambda or theta or whatever. We call them tau of lambda or theta or whatever. So we did talk about estimating this, and we had that an estimator, we could take an estimator to be the sample mean x bar. This is an unbiased estimator for this tau of lambda, which is 1 over lambda. Because the sample mean is always an unbiased estimator for the true mean of the distribution. So we talked then about now trying to estimate lambda itself. I could have so many things here. I could have things that make no sense at all. It's just not a good estimator. So we're talking about properties of estimators, things we would like to see, like unbiasedness and small variance. The lambda is the mean flipped over. So we tried 1 over x bar, but the expected value of 1 over x bar is not 1 over the expected value of x bar, which would then be 1 over lambda, which would give you lambda, because expectation is a nice linear operator, but it doesn't go through more complicated functions like reciprocals that way. But we thought we would try it and see if we could adjust it. So we used the fact that this is actually n over w, where w is the sum as I goes from 1 to n of the xi. And we know that if you're adding up iid exponentials with rate lambda, you get a gamma distribution. The first parameter is the number of things you added together, and the second is the same as the parameter for the exponential. I do, in fact, know the distribution of x bar. I'm not going to use it, but you certainly can. You might recall that we showed when we were talking about the G inverse transformations in the 4 important tools for MathStat, that if we have something with a gamma distribution and we have a positive constant, then C times that random variable has a gamma distribution, and the constant ends up underneath the second parameter. So because the sum of the x's has a gamma distribution, I do know that x bar, which is 1 over n times the sum of the x's, also has a gamma distribution. The first parameter is whatever it was, and then this ends up underneath the second parameter, which is, of course, gamma of n and n lambda. So in the last example and in the last class, I used w as the sum of the x's and used the fact that that had a gamma distribution, and I just let the n sort of float around and took care of it. But I could have gone straight for a gamma distribution for x bar rather than reducing x bar to a constant times a sum. So that's just for your information, but I am going to stick with this because I'm kind of just finishing out an old example that we did. So we saw that an unbiased estimator for lambda is, I don't know if I called it lambda 1. I think we only had one estimator, so I called it lambda hat. I'm going to call it lambda 1 hat. And this is n minus 1 over the sum of the x's. Another way to write that is to note that this is n times x bar. Oops. So you would have n minus 1 over n x bar. But this was our unbiased estimator. I'm going to stick with the first way of writing it here. And so the expected value of this is lambda. Okay, we have this w, which is the sum of the x's, and we had a few computations that I'm going to need to dig into again. We showed that the expected value of 1 over w squared, which is something we needed for computing the variance of our unbiased estimator, we showed that this was 1 over n minus 1, n minus 2 times lambda squared. And we saw that the variance for lambda 1 hat is 1 over n minus 2 lambda squared. So I'm just like writing these down from last time because we already spent a lot of time on this example. So if this doesn't make sense, please check out the last video of the last class. But here is something, here's the new thing. So I had part 1, 2, 3, 4, 5. I'm not sure where I was. This is the next part of the example, like maybe 6, but I don't really know. So I'll just write new question here in this same example. I want to consider estimating lambda with, so the sample mean x bar, its expected value is 1 over lambda. So you might want to estimate lambda with 1 over x bar. So I'm going to call this lambda 2 hat 1 over x bar. Now we already know this is biased, so maybe we don't want to do this. But I just wanted us to have a little practice with mean squared error because we really haven't had to deal with that. Actually, if I go back up here, I can say that the mean squared error for our first unbiased estimator, because it is unbiased, this is the same thing as the variance, which we have computed. But let's get the variance and or mean squared error for this biased estimator. Okay, the variance, actually, before doing that, let's note that lambda 2 hat, which is 1 over x bar, if you compare it to our lambda 1 hat, which looks like this lambda 2 hat is actually n over n minus 1 lambda 1 hat. Go back to the lambda 1 hat. Oops, it's up there in the upper left circle. So if I divide by this n minus 1, that'll cancel that one out, and multiply by n, that'll put an n up here, and we will have the 1 over x bar. So with that, realize that we have done most of all of the work here. Let's find the bias, or let's find the expected value. So the expected value of lambda 2 hat is the expected value of n over n minus 1 times lambda 1 hat. And we can pull out the constant, and we get the expected value of lambda 1 hat. But lambda 1 hat was an unbiased estimator. So that is the expectation for this new estimator. The bias for this new estimator is its expected value minus the thing we're trying to estimate. So this is like how far off we are on average from the true thing. And let me move this down just a little bit. This is n over n minus 1 lambda minus a single lambda. And I can pull out the lambda and put this stuff together, and I get n minus n. I'd get 1 over n minus 1 lambda. So that's the bias. And the variance. Let's look at the variance for lambda 2 hat. Rather than do this from scratch, I'm going to use this fact again, that we've already computed variance for the lambda 1 hat, and we have this nice relationship. So this is the variance for n over n minus 1 lambda 1 hat, and we can pull out constants, but from variances, constants come out squared. And we do have the variance for lambda 1 hat up here. It's 1 over n minus 2 lambda squared. So this is n squared over n minus 1 squared, n minus 2 lambda squared. So that is the variance of our second estimator for lambda, which is biased. So there isn't really a good direct comparison. I wouldn't compare this to the variance for, well, actually I would, because you might accept bias if it gave you smaller variance. But right now I'm just doing computational stuff and not really trying to determine which estimator is best here. Final thing, the MSE, the mean squared error for lambda 2 hat. One way to do this, which I'm not going to do, is to say this is the mean squared error for, well, what is lambda 2 hat? It's 1 over x bar. And the definition is the expected value of 1 over x bar minus the thing we're trying to estimate squared. And you could just square this out and power through it. And you are going to use the gamma distribution to do some of those expectations in there. But we already have most of the work done because we have this relationship. So this MSE is the variance for lambda 2 hat plus the bias squared. And we just wrote these things down. So here's the variance. And here's the bias, which I'm going to square. So they'll both have a lambda squared. So I'm going to go ahead and pull out a lambda squared. And I'll have n squared over n minus 1 squared, n minus 2 plus 1 over n minus 1 squared. So there is the mean squared error for our biased estimator 1 over x bar. And I guess the point here is, especially in a course, like in an exam or homework, when you've got parts A, B, C, D, and don't try to reuse parts that you've already computed. You don't have to reinvent the wheel and do those long integrals or even integrating without integrating. Often you can get away with using other pieces of the problem where you've already done computations. In this class, I don't care if you simplify, except if your goal is maybe to put two mean square errors next to each other and compare, then it would probably be helpful to simplify. But we've been in this example long enough. So is everybody okay? Cool. We do have that the expected value of our lambda 2 hat, while it's not lambda, it is something that approaches lambda because n over n minus 1 goes to 1 as n goes to infinity. So as the sample size gets really large. And I think I might have mentioned this last time, but I'm going to write it again. This is a definition. An estimator theta hat for theta is an asymptotically unbiased estimator for theta if the limit as n goes to infinity of the expected value of theta hat gives you theta. So if you get rid of this, it's unbiased. If you put that limit in, it's asymptotically unbiased. And certainly anything, like if this is already theta, if it's unbiased, then the limit is still theta. So something that's unbiased is also asymptotically unbiased, but not the other way around. And as a point of notation, you might think it's a little weird to look at a limit and not really see an obvious n. Our estimators are functions of the data, and they usually depend on n. You could have a really bad estimator. You can say, I'm going to estimate lambda with x1. I'm going to ignore the rest of the sample. And so that doesn't depend on n. But for the most part, our estimators do depend on the sample size. So our theta hat is generally a theta hat sub n. We just don't see that notation. So you might want to write it in this sort of expanded notation, especially when you're writing something like this, where you're talking about a limit. Anyway, the particular example, so in the previous example, we had that our lambda 2 hat was 1 over x bar, and the expected value of lambda 2 hat was, what was it? Let's go up here. It's right here, n over n minus 1 lambda. So this goes to 1 as n goes to infinity. So our lambda 2 hat is an asymptotically unbiased estimator for lambda for the exponential distribution with rate lambda. Just being a little sloppy there. Another good thing to notice is that the variance for this unbiased estimator is, so look at this coefficient. If you were to multiply out the denominator, you would have a degree 3 polynomial. You'd have an n cubed plus some other stuff, and you have a degree 2 polynomial in the numerator. So the variance of this biased estimator is going to 0, which is also something you would want out of a good estimator. You would want it to get better with a bigger sample in the sense of smaller variance. The MSE as well, this is also, once you put that together, you can see that that is going to go to 0 as n goes to infinity. So the mean squared error goes to 0 as n gets large. So our 1 over x bar is asymptotically unbiased, and its variance goes to 0, and its MSE goes to 0. So there's lots of good things about it, but our lambda 1 hat for this example, which was n minus 1 over the sum of the x's, is already unbiased for finite samples, and its variance goes to 0. And its MSE, which is the same thing as variance goes to 0. So I would still prefer that estimator. But this has all been about just some computational examples with MSE versus variance and bias. I guess I said I was in the example, then I wasn't in the example. Let me write this down. I want to do one more estimator in here. So just to be clear, I am in this exponential example with rate lambda. And suppose that I want an unbiased estimator of the mean of the distribution, so 1 over lambda. We already saw that, well, x bar does it, right? So let's call this tau lambda hat 1 is x bar. But here's another tau of lambda hat, or you can just put the hat on the tau part. This is the same thing as this, but different than putting the hat inside. I'm going to call this tau lambda hat sub 2. I am going to find an unbiased estimator based on the minimum. There is no reason you would do this, like just as a natural step, but maybe in a homework problem, if I said, find another unbiased estimator based on the minimum. So let me write that down because otherwise you wouldn't do this. Find another based on the minimum in the sample. The minimum of exponentials is again exponential, and the rate is n times the original rate. So this means that the expected value of the minimum, the expected value for an exponential distribution is 1 over the rate. And so if I want to get 1 over lambda, that's what I'm trying to estimate in an unbiased way, I need to move this n to the other side. So going back to here, an estimator that is unbiased for 1 over lambda based on the minimum would be n times the minimum. Here is a second unbiased estimator based on the minimum. Kind of unmotivated, but not completely. The reason I looked at the minimum is because it's something we can work with. We know the distribution. This was pretty easy to do here. I didn't have to do an integral to get the mean, and to adjust it was pretty easy. So let's just look at the variance of this, because I think this is really a bad idea. This is an unbiased estimator, so on average it will be lambda, but the minimum in the sample for the exponential, especially if you have a large sample, is just going to be going and pressing up towards 0. Like the minimum is going to be maybe a good estimator of 0. But when you multiply it by n, and if n gets large, you've got like a 0 times infinity kind of thing, at least in the limit. So I think this is kind of maybe unstable. I don't think it's going to give me a lot of information about lambda because it's just trying to be zero, but the sample size increasing is trying to compensate for that. So let's check out the variance to see how bad this is in terms of variance. I am going to pull out the constant and it comes out squared. And now I'm going to use the fact that I know or can look up the variance of the exponential distribution. If you have an exponential random variable with rate parameter lambda, the variance is 1 over lambda squared. So this is 1 over n lambda squared because the parameter here is not lambda, it's n lambda. And when you square things out, you get 1 over lambda squared. And look at that. That is a variance that is not moving at all as the sample size gets large. That can't be good. You definitely want things to get better when you have more information, when you have more data, when you have a bigger sample. So yeah, maybe not so good of an estimator, but we are going to eventually have techniques for finding estimators. Right now, I'm kind of all over the place. Let's try one based on this or based on that. Let's try a common sense estimator. If we want to estimate the mean, use the sample mean. Um, right now, you don't really have methods for coming up with these other than a few common sense things and me telling you make your estimator based on a given statistic. We're still going to have to do this for a while, but eventually we're going to get away from that and you will have actual methods for finding estimators. But we have just talked a few times about what happens here as n gets large. Some of our estimators are asymptotically unbiased. The expectation may be the true lambda or the true theta to begin with, in which case it stays that way in the limit. It might not. It might have like an n over n plus 1 in front of the true theta or the true lambda, in which case it approaches the true theta or true lambda in the limit, so asymptotically unbiased. And we have a lot of variances going to zero, which seems good, predictable estimators as your sample size gets larger. But for the rest of today, I do want to talk about convergence for what we're seeing here. Our estimator theta hat of a theta, which probably depends on an n, is like a sequence of random variables. And we need to talk about what it means to take the limit of a sequence of random variables. So let's ignore estimators. Let's leave them behind for a little bit. Let's talk about a sequence of just straight up looking random variables, x1, x2, etc. What is the limit as n goes to infinity of xn? This is not something we can handle just yet because these are not numbers. We know how to take limits of sequences of numbers, but these are potential wannabe numbers. They're all over the place. And we can't make sense of a statement like this until we use probability, maybe an expectation, maybe computing a certain probability involving xn, to turn this into something involving actual fixed numbers. So our first type of convergence, I guess you can call our asymptotic unbiased thing, that seems like a very weak type of convergence. Um, if these things are asymptotically unbiased, you might say that the sequence is going towards that point. I will come back and talk about that later. That's not actually the one I want to talk about today, but it is kind of weak in the sense that it's just like one little part of the sequence, just the mean, maybe going to the right place, but there are so many other things going on with distributions. So for today, I want to talk about something known as convergence in probability. We're going to have several types of convergence and reasons for wanting several types of convergence. So right now, this is just going to be a definition. A sequence of random variables, x1, x2, etc., converges in probability to a random variable x if Here comes the analysis looking stuff. For any epsilon greater than 0, if we look at the limit as n goes to infinity of the probability that the absolute value of xn minus x is greater than epsilon, right? So this is the distance between xn and x, and we want that to be getting small if the sequence is converging to this. So we want that distance to be so small that no matter what little epsilon you choose, this distance will be greater than that with probability 0. It will just not be. This distance is getting so small that eventually it will not at all be allowed to be greater than epsilon. So 0, this is one way to define convergence in probability. Equivalently, we can talk about the probability that this distance is less than or equal to some epsilon, and it's definitely going to get less than or equal to epsilon eventually. So this will happen in the limit with probability 1. These, the strictness of these inequalities, not important because this is a for any epsilon problem and a for n large enough. So you'll eventually be able to get strictly below something or strictly below above something. It's not going to matter whether I put equalities or strict inequalities on these. Okay. So we have notation for this. If this happens, we're gonna write xn and then an arrow to x and then a capital P on the arrow. This is convergence in probability. I still want to stick with random variables, but just a little spoiler here. For us, we're going to be talking about sequences of estimators converging in probability to an unknown parameter. And our unknown parameters are not random variables. So here I have random variables converging to a random variable, and here I have random variables converging to a constant, and that is fine because a constant is just a boring random variable. You can let x equal 3 with probability 1 and anything else with probability 0. So beta with probability 1 and anything else with probability 0. Constants are just special cases of random variables. We want to be able to show convergence in probability for things, and this means that we're going to need to take some limits. By the way, this is a sequence of numbers, right? That's what I was saying at the beginning. This is a sequence of numbers, so this limit makes perfect sense to us. We've sort of taken the randomness out before taking the limit. So I have some inequalities that I think are going to be useful for us for showing convergence in probability. And we're going to use them for other things as well. So I wouldn't ignore this list of inequalities and just say, okay, well, in the end, we used it to prove this theorem, and that's what I'm going to use to show convergence in probability, because I think these inequalities are going to be useful for you down the road for other things as well. Okay, so the first, I'm going to have 3 or 4 here. I'm not sure yet whether I'm going to do the fourth. The first, I'm going to let x be a random variable. This is discrete or continuous. And g of x, a non-negative function. Let's say real value, be a little more specific here. For any constant, lowercase c greater than 0. So this is just a real number. This is not a random variable. We have this inequality that says the probability that g of capital X is greater than or equal to c is less than or equal to the expected value of g of capital X over c. This inequality doesn't really have a name, but I and other people definitely call this the generalized Markov inequality. This will make sense after I do the second inequality, which is Markov's inequality, which is a special case of this. So this is more general than something coming up known as Markov's inequality. let's prove it. Before proving it, so I have some notation for you for this proof and beyond that I think is going to be quite useful. Two things. One is integrating PDFs or other functions over sets. Over sets. So as an example, the integral from 0 to 1 of like an f of x dx plus the integral from like 5 to 7 of an f of x dx, we can write this as integrating over a set A where A is the, in this case, union of these intervals, which is a subset of R. It allowed us to write a sum of two integrals more compactly, and it's going to get a lot worse. Like, suppose you have, just as another example of this, suppose you have x, a random variable, let's assume it's continuous, on 0 to infinity. And suppose you want to find the probability that the sine of x is greater than 1/2. Let me draw sine over here. So here's 1. It's equal to, it's okay if you don't recall this from trig, but it's equal to 1/2 at pi over 6 and at 5 pi over 6. This is pi. This is 2 pi. The next one here is going to be, where it's equal to 1/2 is going to be pi over 6 plus 2 pi. That's going to be 13 pi over 6. And the next place where it's 1/2 is going to be 17 pi over 6. So my point is this. Going back to the probability, this is the integral from pi over 6 to 5 pi over 6, the PDF for x, plus the integral from 13 pi over 6 to 17 pi over 6, the PDF, plus, and we'd have to go on forever finding all those intervals where x needs to be for the sine of x to be greater than 1/2. However, it's easier not to do the integral, but to write the probability that the sine of x is greater than 1/2. This is just going to be the integral of the PDF for x integrated over the whole set of x's for which sine of x is greater than 1/2. I guess, yeah, I was going to say I need to restrict this to x greater than 0, but I don't, because my PDF will have an indicator in it that will cut us off and not pick up the negative x's in this set under the integral. So, that doesn't look nearly as nice as an integral over a set A, but it's really the same thing. So that's number 1 in my notation. Actually, that's number 1 and 2. So this, my second one. Number 1 is just to use a set to describe summing integrals over many regions that could get very weird. They don't have to look, like contiguous parts of regions. And the other one is talking about finding probabilities for a function of a random variable by not solving for x first, which is kind of what we did at the beginning of the course, but integrating the PDF for x over a funky region that is easily described with this kind of set notation. So with that, we are ready to go back and prove this. First I'm going to remind you, G is non-negative. C is a real number that is non-negative. And this inequality, I am going to start with this expectation. I'm going to start with this expectation of G of X. As usual, X could be discrete or continuous, so this expectation is going to be a sum or an integral. I'm just choosing to write integrals, but if X was discrete, you could do the same exact thing with sums. So this is the integral over the whole world minus infinity to infinity of g of x times the PDF for x dx. And looking towards what I want to see and the probability we just talked about with the sign, I am going to break this up. I'm going to integrate over all x such that g of x is greater than or equal to c, and then the other integral over the rest of the x's. So I'm going to integrate over all x's for which g of x is less than c. I am going for an inequality. Let me remind you of what that looked like. You can kind of see something coming up here, especially in light of our conversation about that sine function. I am going to drop the second integral. A PDF is always non-negative, and my g was assumed to be non-negative, and that means this whole thing is greater than or equal to 0. So if I drop it, the next line is going to be smaller. So this line is greater than or equal to the first integral on the line above. And for the x's that I'm running over, g is always greater than or equal to the constant c. So this is greater than or equal to the integral over the same set, but I'm going to put c in for g of x to get something smaller. And then if you pull the c out, what you're left with is integrating the PDF for x over a region. And we just talked about how this is a way to write down the probability that g of capital X is greater than or equal to c. So if you pull it all together, we have this expected value is greater than or equal to this. If you divide by c, because c is positive, it's not going to flip anything. And you will end up with this probability less than or equal to the expectation over c. And that's what we wanted. So we are done proving this inequality. Okay, so it's time for Markov's inequality. And this says for any random variable x. Now, if you look up Markov's inequality, you might see any non-negative random variable x. Sometimes it's stated that way. I'm going to have absolute values around all the x's in the statement of the inequality. And any real numbers c and r greater than 0, we have the probability that the absolute value of x is greater than or equal to c is less than or equal to the expected value of the absolute value of x to the r over c to the r. Again, you could not have the absolute values as long as x was positive. So again, you might see it written that way. Let's prove it. I'm going to start with the left-hand side. The probability that the absolute value of x is greater than or equal to c. I want to get the r's in this, so I am going to raise both sides to the rth power. Here's where r greater than 0 is important, because if you raise something to a negative power, that's like, like if a is less than b, a to the -2 is actually 1 over a squared. It's going to flip the inequality. That's what I'm trying to say in a long-winded way. But because r is greater than 0, this is okay. And now this is like the g of x from the previous inequality, and this is like the c from the previous inequality. So this is less than or equal to the expected value of g of x, which is absolute value of x to the r over c, but c is now c to the r, so we are done. Markov's inequality came first, and then later it was generalized, obviously, I think, obviously. But that's all there is to that one. Next up, we have Chebyshev's inequality. Just to remind you what we're talking about today, convergence in probability for a sequence of random variables. And these inequalities will help. because we're going to take limits of certain probabilities. And if we could say those probabilities are above something or below something and use like a squeeze theorem on the limits, that's how we're going to get most of our convergence and probability results. So Chebyshev's inequality is much more specific, I guess. I don't know if that's the right word, but it depends on more of the underlying distribution of X. So suppose that X is a random variable from a distribution with mean mu, so mu is the expected value of X, and variance sigma squared, which needs to be finite for this to make sense. For any k greater than 0, now most people use k's. I'm not sure why, because that looks like an integer, but this is a real number. Could be an integer, I guess. The probability that the absolute value of x minus mu, closed absolute value, is less than k times sigma. This is greater than or equal to 1 minus 1 over k squared. So there's another way to write this down, but this sigma is the positive square root of sigma squared. And it's called, in statistics, a standard deviation, which you'll use that a lot if you actually work with data. In math stat, not so much. We're usually working with the variance. But variance is a measure of spread of a distribution, and it involves some squares of things. And so if you're working with actual data with some meaningful units like dollars, the cost of something, then when you compute a variance, it's not in the units of the original problem, it's squared. So people like to take the square root and look at the standard deviation so that they're speaking about everything relative to everything in one unit. But it's also a measure of spread. If the variance is large, the standard deviation is large, vice versa. So one way people, or you can interpret this, is you can say the probability that X is within K standard deviations of its mean is at least or greater than or equal to 1 minus 1 over k squared. Chebyshev's inequality. Okay, there's one other way you might see Chebyshev's inequality stated, or that you might want to use it because it's more convenient for you. Equivalently, I can flip this both sides around. So like I've got, if you have an a greater than or equal to a b, and these are numbers between 0 and 1, then 1 minus a is less than or equal to 1 minus b. And that's basically what I'm going to do with this inequality up here. But when you do the 1 minus of a probability, you're talking about the complement of an event. So first I'll just do the 1 minus, following this down here. 1 minus the probability that absolute x minus mu is less than k sigma. This is less than or equal to 1 minus this, which is 1 over k squared. However, this 1 minus, using the complement for probability, this is saying the probability absolute x minus mu is greater than or equal to k sigma is less than or equal to 1 over k squared. I'm writing so huge, but these are two ways that Chebyshev's inequality is written. And the inequalities here being like strict here and non-strict here are important. It's important to respect those inequalities because Chebyshev's inequality can be used for discrete random variables. So if you have continuous random variables, it won't matter, but for discrete random variables, it will. And unlike our definition of convergence and probability, we're not taking any limits. So it's not like Are you less than or equal to this? Eventually you'll be less than, so it really doesn't matter. Nothing's moving in a limit, and things could be discrete. So the strict or non-strict inequalities are important to pay attention to here. So let's prove it. We've got it proven, really. It's another application of the generalized Markov inequality. And this is something we're going to be using a lot for convergence in probability because we have a random variable, theta hat, minus its mean, theta, if it's an unbiased estimator. So this sort of thing. We'll try it in just a couple of minutes. I think I will go for the second one because it's right here, the one I've circled here. The probability that the absolute value of x minus mu is greater than or equal to k sigma. I want to try to use my first inequality, which was that the probability that g of x is greater than or equal to c is less than or equal to the expected value of g of x over c, as long as g is a non-negative function and c is a non-negative real number. Why don't I do this first? Because I've got standard deviations and I want to turn them into variances. So this is the same as the probability that x minus mu squared is greater than or equal to k squared sigma squared. I have squared both sides and I don't have any issues because k is positive and sigma is the positive square root of sigma squared. So I get the exact same thing. Whereas in general, this is going to be like you're going to have to consider maybe a plus or minus kind of thing happening and get a sort of a sandwiched inequality on both sides. I can rewrite this way here because k and sigma are positive. And now this is going to be my g of x. Mu is in there. It's just a constant. You know, it's like g of x equals 3x. You're not going to call that a function of x and 3. So mu is a constant, just like 3 is a constant. And I've got this as my new c. So I'm going to use this. And continuing from here, this is less than or equal to the expected value of x minus mu squared over c, which is k squared sigma squared. But that numerator is the variance for x. So this is sigma squared over k squared, sigma squared, and we get cancellation to 1 over k squared. So I have this less than or equal to this, which is what I was trying to show. Okay, I have a fourth inequality. It's called Jensen's inequality. I'm going to push that off until later. We're actually not going to need it until much later in the course. I just thought I would throw it in with the list of inequalities. But because I'm running out of time, I want to get back to convergence and probability. So Jensen's inequality is on the back burner. Okay, back to convergence in probability and actually a theorem, a big theorem known as the weak law of large numbers, which is abbreviated as WLLN. I'm going to let x1, x2, etc. be IID, independent and identically distributed from any distribution, so the same distribution because they're identically distributed, with mean, mu, and variance, sigma squared, that needs to be finite. We haven't really talked about it, and I don't want to do the aside, but sigma squared being finite implies that the expected value of x squared is finite, and that actually implies that the expected value of x is finite. We could show this, it's not that hard, but in this line here, I'm also saying the mean is finite. The one that's more difficult to be finite, because you're squaring things, is the variance. So if that's finite, the mean is definitely finite. Okay, so that's not a theorem. What's the punchline? We're going to look at the sample mean, x bar, And I claim this converges in probability to the individual true mean of the distribution. And you might see this written as an xn bar. There are n's in here, right? It's 1 over n times the sum from 1 to n. But if you think it's weird to have that convergence arrow and not to see the n, then by all means write it out like this. This is huge. We're going to use this a lot. This is going to get us a lot of convergence and probability results really, really quick. You can just take any distribution in your table and say the sample mean converges to, in probability, converges to, just go to the mean column, grab that, whatever it is. And now you know a ton of convergence and probability statements. To prove this, I am going to use Chebyshev's inequality on the sequence of random variables xn. So again, x bar. The x bar is really dependent on n. So first I average one of them, which is just x1, then I average two of them, x1 and x2, then I average three of them. So that's how I'm forming the sequence. And and before I go on, the weak, this convergence in probability, this epsilon definition, is just one way to talk about a sequence of random variables converging. And we're going to see that we're going to have several methods, and that some of them are stronger than others, and some of them are weaker than others, in the sense that if you have this convergence type and it implies this other convergence type must hold, but not the other way around, then the first convergence type is stronger. And this convergence and probability is actually for us going to be one of our strongest types of convergence, but it is weaker than other types of convergence. So we'll get there and talk about this. But the word weak has to do with convergence and probability being a weaker form of convergence than something known as almost sure convergence. But I digress. Let's prove it. Let's use Chebyshev's inequality. I am going to use it, I think the first version, the probability that a random variable minus its mean, that this is less than k standard deviations, is greater than or equal to 1 minus 1 over k squared. So this is just me restating it because there's no x in this problem. You know, there's an x1, an x2, and an x bar. But I just want to translate this to our random variable x bar. And I would subtract the mean for x bar. And I would use the standard deviation for x bar. By the way, this statement is for any k greater than 0. This is greater than or equal to 1 minus 1 over k squared. So I know this is true. This is just Chebyshev's inequality, but I've gotten a little more specific about what the random variable is and used a different notation. And we know that this mean is the same as mu, the original mean. And we know that sigma x bar squared is the original variance over n. So we know the standard deviation, the square root of that, is sigma over the square root of n. So what this is saying in this notation is the probability absolute x bar minus mu less than k sigma over the square root of n is greater than or equal to 1 minus 1 over k squared. So that is just Chebyshev's inequality written down one of our directions and restated in the specific context of the sample mean. So now I want to show convergence in probability, which means I'm going to take an epsilon greater than 0 and fix that. And I want to consider the probability that the absolute value of x bar minus mu is less than epsilon. We're going to take a limit as n goes to infinity. There is an n hidden in the x bar, and we want this to go to 1. Please don't try to memorize one of those convergence and probability statements versus the other. This is supposed to be approaching this, which means this whole thing is supposed to be getting small. Definitely smaller than any epsilon. Definitely, with probability 1. So that's why I know this is supposed to go to 1 and not 0. And I could rewrite this as the probability of, right now I want to rewrite it so that I can use Chebyshev's inequality. So I can rewrite this as the probability that x bar minus the mean mu is less than k sigma over the square root of n if we take k to be the right thing, and we're allowed to choose any positive k. So I want to take k so that this is equal to this. which means I want to take k to be epsilon square root of n over sigma. That's how I can get this equal to this. And I'm allowed to choose any k for Chebyshev's inequality. So I know this is greater than or equal to 1 minus 1 over k squared. My k is epsilon square root of n over sigma. This is 1 minus sigma squared over n epsilon squared. Let's take a limit. The limit as n goes to infinity of the original probability, that's towards the upper left right now, less than epsilon, this is greater than or equal to the limit as n goes to infinity of 1 minus sigma squared over n epsilon squared. And because sigma squared is finite, as n goes to infinity, this goes to 0. We might have a problem if sigma squared was infinite, and we'd be talking about something infinite over something going to 0, uh, over something going to infinity. But we don't have that problem here. This is 1. So what do we have? We have this limit is, meant to get that inequality in there. We have this limit is greater than or equal to 1, but probabilities cannot be greater than 1. So this implies that the limit as n goes to infinity, the probability x bar minus mu less than epsilon must equal 1. Kind of running out of time, but I would write because probabilities cannot be greater than 1. So I definitely had time, but this is a one-liner. If I go back to the exponential example, and I ask you, to what does x bar converge in probability? You would say by the weak law of large numbers, it converges to the mean of the distribution. The mu here is the expected, I said it was a one-liner, but this is 1 over lambda. So we know that x bar converges in probability to 1 over lambda by the weak law of large numbers. Boom, easy as that. We're gonna know a lot of statements about convergence and probability now that we don't have to do from scratch with epsilons or Chebyshev's inequality. But I am out of time. So yeah, next time we are going to hit a new type of convergence called convergence and distribution. But before that, I am going to have a couple of very exciting theorems to help you establish convergence and probability quickly when you're not talking about a sample mean, because we have a quick way to do that. But we're going to be talking about other types of estimators that are not X bar. So it's going to be awesome. I hope to see you in the next one.